In this lecture, we'll look at the performance of systems that have multiple levels of cache. So multiple levels of cache are adopted in pretty much all modern architectures because the difference in the access time and the throughput in the L1 cache and the memory is very big. So we need these additional levels of cache so that we can make each level larger than the previous level, but also because it's larger, it will be slower than the previous level. So the primary level of cache that's attached to the processor, it's usually in the same chip as the processor, is small, but is very fast. The second level of cache, that L2, will be a reference for all the misses from the primary level. It's larger, but it's slower, but it's still faster than main memory. And so initially the systems would have a single level of cache in main memory, then they had L1 and L2, and then L3 was introduced, and more recently L4 has been introduced in some of the high-performance computer systems. So the main memory will service the L2 cache miss in a system that only has 2 levels. Of course, if there are 3 levels, then L3 will serve the misses from L2 and so on. And so some considerations for multi-level of caches. The primary cache will focus on the minimal heat time. So the primary level cache will be designed in such a way that every access can be completed in one cycle. Therefore, the limitation in practical design for the primary level of cache is the longest distance between the processor and the cache entry that's at the farthest place in the cache. So that distance will limit how big the primary level of cache can be. The second level of cache will focus on having a low miss rate to avoid main memory accesses, and the heat time has less overall impact because you only gonna access the L2 cache after you have missed the L1 cache. You can think that the L1 cache will filter the most frequent accesses and will always serve the processor the access that have the highest locality, and then as you go down in the levels of cache, you have accesses that are more difficult to find. The L1 cache block size is usually smaller than the L2 block size. So let's look at an example of a system with 2 levels of cache. So we have a processor that is running at a clock rate of 4 gigahertz. Has a base CPI, so that's the average number of clocks per instruction of 1, when all the references hit in the L1 cache, so when there is no delay because of memory accesses. The main memory access time in this processor is 100 nanoseconds, and the L1 miss rate is 2%. The question that we want to address is how much faster will the processor be if we add an L2 cache that has a 5 nanoseconds access time for either a hit or a miss, and is large enough to reduce the miss rate to main memory to 0.5% of the access to L1. And we'll assume that all the accesses in this problem are instruction fetch. So we don't have the issue that some of the access will be data fetch and will happen parallel with instruction fetch, because we want to focus on the effect of adding the second level of cache. So we have the processor, we have the L1 cache, and we have the memory. Again, we can assume that we are executing 1,000 instructions. That number is arbitrary. You can assume any number and it will gonna work fine. The processor runs at a clock rate of 4 gigahertz, so we can compute the clock cycle as 1 over the frequency, so that will be 0.25 nanoseconds. The base CPI is 1, so the L1 cache cycle will be cache access will be completed in 1 cycle. The main memory access time is 100 nanoseconds. And we have that the L1 has a miss rate of 2%, so of those 1,000 instructions, 20 will be sent to the main memory. So I can compute the CPI with no L2 as the total number of cycles that you need to execute the instructions plus the number of cycles that you need to access the memory in the case that you have misses. So that will be 20 times 400. And I divided by the total number of cycles to give me 9 cycles per instruction. So I have a CPI of 9 because of this memory hierarchy. Now I introduce a second level of cache. My 20 requests no longer go to the main memory, they go to the L2 cache. And the L2 cache has an access of 5 nanoseconds, so I had 5 nanoseconds in the L2 cache. And the miss rate to the main memory is 0.5. So I have is 50%. No, it's 0.5%. So I have 5 requests going into the main memory. And so it's 0.5 of the L1 accesses. So this is an important detail. Let's go back. This 0.5% is in relation to the L1 accesses. So it's giving me a global miss rate. It's not a local miss rate. The local miss rate for the L2 cache, if I want to compute, will be the total number of access that miss divided by the total number of access to the L2. So it will be a 25% miss rate in the L2. That will be the local miss rate for the L2. But the problem gave me the miss rate of the L2 in terms of the accesses to the L1. That's why I got the 5. That was 0.5% of 1,000. So now the CPI for L2 will be the 1,000 cycles that I need to execute these instructions here in the L1. Plus 20 times 20 because I have 20 requests that each one of them requires 20 cycles in the L2, plus 5 times 400 because I have 5 accesses that will require 400 cycles in the main memory, and that gives me a CPI of 3.5. So comparing with the previous, that was about 9. So the local miss rate of L2, as I point out, would be 25%. So the CPI with no L2 was 9 cycles per instructions. When I introduced L2, it was 3.4 cycles per instruction. The power processed with L2 is 2.6 times faster than the process without L2. And that was the motivation to insert multiple levels of cache. I can solve the problem, the same problem here. So the base CPI is 1, the clock rate is 4 gigahertz, the main memory access time is 100 nanoseconds, and the L1 miss rate is 2%. I can simply compute the clock cycle as I did before, and without the L2 cache, only with L1, the miss penalty will be the memory access divided by the clock cycle, so it's 400 cycles. And the effective CPI with no L2 will be 9 cycles. So I'm just showing how I can solve the very same problem using only the mathematical relations without doing the drawing that I did in the previous slide. And now that I inserted an L2, what I have is that the L2 penalty will be the L2 access time divided by the clock cycle. So the L2 access time is 5 nanoseconds, so it's 20 cycles. And the memory penalty for the L2 is the memory access time plus the L2 penalty, which will be 420 cycles. So with L2, I have 2% minus 0.5%, which is 1.5% of the access hit L2, and 0.5% of the access go into the main memory. So I can plug these percentages as I did here in the slide. The 1.5% is in here, the 5%, the 0.5% is in here, and that gives me the 3.4 cycles. So the power with L2 is, the process with L2 is 2.6 times faster. I just illustrate a different way of solving the same problem. Some iterations with advanced CPUs. Advanced CPUs, as we discussed in previous lectures, execute instructions out of order. And because they have out of order execution, they can execute instructions while we are processing cache misses. So most of the caches that are designed, pretty much all caches that are designed today, they all memory systems, they can have a hit under miss, which is if I had a previous miss and I'm waiting for the result to come back from the memory, the cache does not stop operating. The cache keeps accepting requests from the processor. And if you have the data in the cache, you can provide to the processor while you are waiting for the miss. So pending stores stay in the load store unit for this out of order execution. And dependent instructions wait in the reservation stations. Independent instructions continue. So instructions that do not depend on the data that I miss in the cache can proceed with execution. The effect of miss depends on the program data flow. It's much harder to analyze. So usually when we have these out-of-order processors, and especially when we have out-of-order processors with multiple pipelines, that the superscalar machines with very deep pipelines, it becomes very hard to do the analysis for example, the average memory access time that we are doing in these lectures. And the solution is to use simulation. So in Fortune9, we do not use many of these expressions that we are using here that are quite simplified. We use system simulation in order to estimate the performance of the processors. The other observation is the interaction with the software. The misses depend on the memory access patterns. And so when you write code, you may try to write code in such a way that you increase locality so that you reduce the probability of misses. Compilers, when they generate code, they also generate code in such a way to increase locality. One of the best things that you can do in a compiler to optimize code is to increase locality. So, and these access patterns will depend on the algorithm behavior, so which algorithm you choose, on the compiler optimization, and for memory access as well. So here is a graph showing two sorting programs, radix sorting and quicksort. And it shows the number of instructions per item. So the x-axis here is, or the horizontal axis is the number of items that I'm sorting. The vertical axis is the number of instructions per item. And you can see that the number of instructions per item is reducing as the number of items increase. The number of cycles per item reduces for a while for radix sort, but then increases slightly. And the number of cycles per item for quick sort keeps increasing as I increase this size. But now when I use I look at the number of misses per item, so the number of cache misses per item, you can see that radix sort has this effect that after 64 items, the number of misses per item increase significantly. So that is what will make radix sort much less efficient than quick sort for larger sequences. You can see the radix sort in terms of misses per item has kind of a sweet spot around 64 items. So it's just to illustrate that when I wanted to make these relations, the relations, the simple relations that we are using in 229 are just a first approximation. And when I need to actually analyze a modern system, I'm going to have to be based on system simulation for my estimates.